In this video, we're giving an introduction to the radian as a unit of angle, and I'm going to give my perspective on why we call radians the natural unit of angle. And the starting point here is to take a look at the arc length of a sector of a circle. So there's a sector of a circle, that's a slice of pizza if you like, and this circle has a radius of r, a subtended angle of theta, and an arc length, that's the length of the crust on the slice of pizza in this metaphor, is given by s. And we want to establish a relationship between these three variables s, r, and theta. So we start thinking in terms of proportionalities. So first we ask, how does the arc length depend on angle? And the answer is pretty obvious here. If we double the subtended angle, then we have twice as much arc traced out. In other words, 2 slices of pizza gives us twice as much crust. So we can conclude that s is proportional to theta, and we're starting to build our formula for the arc length. The second relationship isn't as obvious. What happens to the arc length if we double the radius of the circle? So one way to approach this question is to remember that the circumference of the entire circle is given by 2 pi r. So the circumference doubles when the radius doubles. That means twice the amount of arc for the entire circle, and therefore twice the amount of arc for any given sector on the circle. Or continuing the pizza metaphor, a slice with twice the radius actually has exactly twice the length of the crust. So there's our second proportionality. The arc length is proportional to the radius. So now we've established that the arc length is proportional to the subtended angle theta and to the radius of the circle r. And this is the moment we're going to make a choice that defines the radian. I'm going to say, let's make the simplest possible formula for arc length that captures these two proportionalities. And that's just s equals r theta. Now this choice has the consequence that we've already chosen some interesting units for angle. Consider the arc length of an entire circle. That's the circumference, or c equals 2 pi r. If we compare that formula to s equals r theta, the circumference is just the arc for an entire circle. I have the radius of the circle appearing in both of these formulas, and then I see that theta must be equal to 2 pi for the entire circle. So the angle subtended by an entire circle is 2 pi, and this means the units of angle that we've implicitly chosen already are radians. In other words, the units of angle for which an entire circle has an angle of 2 pi. Now I want to make a couple quick points about radians before we wrap it up. First, if we look at our arc length formula, which again is only valid when theta is measured in radians, that's s equals r theta. We see that the left side of the formula should have units of length, but on the right side, r has units of length, and this means that theta itself must be unitless. So radians can sometimes be written as rad or rad as a reminder, but technically they have no units at all. The second point I want to make is that we do need to be able to convert between radians and degrees because degrees have a lot of practical applications. And this can be accomplished with a conversion factor of 2 pi over 360 degrees or 360 degrees over 2 pi. And we're allowed to do this because 2 pi radians is the same angle as 360 degrees. Now, when I was in pre-calculus, I was taught to use pi over 180 or 180 over pi. And of course, we could obtain that by just dividing the top and bottom by 2. But I prefer to just write it as 2 pi and 360 degrees because it's such a clear reminder of the total angle in a circle. So to give a couple quick examples of these conversions, I want to start by converting 1 radian to degrees because it's useful to remember roughly how big a radian actually is. And as we do this, I'm going to go ahead and write rad for units of radians, just keeping in the back of my mind that they are technically unitless, so you can disappear those units whenever you like. So we have 1 radian, and we're going to multiply by a conversion factor that takes me to degrees. So I need radians in the denominator. I'm going to put 2 pi radians down here, and that's the same thing as 360 degrees up there in the numerator. And our radians are going to cancel. So really all we have to do in our calculator is take 360 and divide by 2 pi. And when we do this, we get approximately 57.3 degrees. So radians are actually a pretty large unit of angle. In the second example, we're asked to convert 30 degrees to radians in exact form. So we start with our 30 degrees, And we need to multiply by a conversion factor that cancels the units of degrees. So this time the 360 degrees is in the denominator and the 2 pi radians is in the numerator. So it turns out that 30 divides 360 evenly. In fact, that's a factor of 12. So if we cancel a 30 in the numerator and denominator and just cancel the degrees while we're at it, I end up with 2 pi over 12 radians. And that reduces further to pi over 6 radians. Notice I didn't write radians in my final answer because radians are technically unitless and I can just disappear them whenever I like. So the final angle here corresponding to 30 degrees is pi over 6. In the next video, we establish the special angles on a circle in both radians and degrees. That video is linked at the upper left, and I'll see you there.